representation of all of these neutrons decaying, and then the electrons and protons combining together to form hydrogen atoms, and the hydrogen atoms are all radiating this
here. This will be quicker.
cosmic background.
Thought I had the other.
Now this temperature was only 3.7 degrees. And this is a representation of a hydrogen atom. And it shows the different links. At the very bottom you have the electron, the classical radius of the electron, and then the next link and the next link, and then the Bohr radius is where the two, the proton and the electron are held together. And the last link in the chain is what it releases the photons.
Looks like an issue.
And the difference in size between the bottom link, the classical radius of the electron, and the Lyman photon at the top is about 32 million times. So you can see it's hard to demonstrate this with a drawing when you have one part that's 32 million times bigger than the other. And up at the top I show the wavelength of what the hydrogen atom produces today, and what the hydrogen atom produced at this time when the electron was only about 150 times less massive than the proton. So the background radiation has not changed. It has stayed the same from the time it was created until now. There's no redshifting of it. There's no cooling off. The universe started off not as very, very hot, but it's very, very cold. It was only 2.7 degrees. You can go to the next one here. And one of the factors of this, as the electron gets less and less massive, it produces shorter and shorter wavelengths. So the universe is really heating up. And there's no real entropy in the universe because it started out very cold and it's getting warmer and warmer. So as the photons dissipate the heat through the universe, the photons produced by atoms are getting hotter and hotter. And this just shows, this is a graph of the cosmic background radiation. It's basically a perfect example of the theoretical background radiation. The more they measure it, the more they find out that it falls closer and closer to the perfect background radiation curve. And also, the cosmic background radiation is the main source of energy in the whole universe. It's practically 99% of all the photons in the universe that we receive are cosmic blackbody radiation. And as far as the energy goes, it has more energy than all the other forms of energy. Like right here in the Milky Way, there's basically three forms of energy. There's the sunlight, or rather starlight. We disregard sunlight. And starlight amounts to about 3 degrees Kelvin temperature. And the background radiation is about 3 degrees, and the cosmic rays are about 3 degrees. Well, 99% of starlight actually comes from the Milky Way, whereas the background radiation comes from the universe at large. So that means that even though the temperature is the same here, in the universe at large, it's about 99 times greater. And the cosmic rays come, a lot of them from the Milky Way, so the universe at large is mostly background radiation. You can go to the next one here.
It's coming.
Yeah. One of the things I passed out some little books which kind of talks about the talk here, but I have another book which it goes into more detail. It goes into nuclear structure and radiation of the hydrogen atom and gravity. And this shows at the time when the background radiation was formed. This shows the spectrum of the hydrogen atom at the time. This is the photons of the hydrogen atom would emit when the electron was at this mass. And it kind of corresponds to the graph of the background radiation. Okay, you could probably go to the next one. But anyway, these books, I have a number of them, and if anybody wants them and is interested, I'd be glad to give them to you. The back part of the book goes into nuclear structure. It has nuclear models of every element. It shows how the protons and neutrons are put together in the nucleus of each element. And this shows basically the kind of the history of the Bohr radius. As the electron changes in mass, it also causes the Bohr radius to change and the fine structure constant to change. And it's these changes that cause the photons produced by the hydrogen atom to constantly get shorter and shorter as the electron mass decreases. And the interesting point about this, if you're using my models, at the point where the neutrons became stable, unstable. The reason they became unstable is because the secondary coils of the electron became larger than the primary coils of the proton, and the electrons couldn't fit inside of the protons anymore, and so this is what caused them to decay. And it's this point where they came apart. Well, it's also, this is the exact point where the hydrogen atom would be producing photons of the cosmic background radiation. So whether or not you want to use my models and system for the hydrogen atom, by using these models, it predicts exactly the temperature of the cosmic background radiation. Because when they split at that time, that's the size of the wavelengths of the atoms of the photons will be. Okay, is that about time?
No, you got more time.
Oh, okay. I don't know what we have left here.
Now you got more than 10 minutes.
Oh, I do? Okay.
But some of that's for questions.
Okay, well then this is another factor. I know there's somebody here that's talking about an expanding Earth. Well, when the electrons were heavier than they are now, the atoms were much bigger. As the mass of the electron decreases, it causes the size of the atoms to decrease because it changes the Bohr radius and they get smaller and smaller. So in the past, millions and millions of years ago, the Earth was actually much larger than it is now. It has the same number of atoms, but the atoms are bigger, and so the Earth is larger. And this explains how the dinosaurs maybe were able to walk around. Now, there's been a lot of study about dinosaurs, and dinosaurs are just too big to be able to walk. They don't have, their bones aren't strong enough to hold them up, and they can float in the swamp, but the biggest dinosaurs wouldn't be able to get up and walk. But if the Earth was bigger, the gravity would be a lot less, and it would allow for the dinosaurs to be able to walk around. There's another factor that the dense